Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to talk about the idea of orthogonality in a vector space. And here we're going to start off with the definition of orthogonality set. We have a set of vectors. So here we have a couple of vectors inside this set. And the set here is called orthogonal if all pairs of distinct vectors that are really different from each other here, so the distinct vectors in the set have to be orthogonal. So what it means by being orthogonal, mathematically it means that if you take the combination of these two distinct vectors, you can see clearly that vi is not equal to vj, and the result of this has to be equal to 0. So that is the definition of vectors being orthogonal. Now, when we talk about the graphic representation of orthogonal vectors, it means that if you, for example, you have this vector here in this direction, so this is vector I, and another vector in this direction, let's say this is vector j, then the angle between these two vectors here is 90 degrees. So that is the graphic representation of vectors being orthogonal. So imagine if you have a set of vectors here. So you need to be able to make sure that you cover all possible pairs. For example, vector 1, vector 2, the result must be 0. You have to check. If it is 0, then it is orthogonal. And you have to make sure, for example, v1 and v3, v1 and v4. So you need to be able to do that systematically and then move on to v2 with v3, v3 with v4, and so on. So that's the idea. You have to check that all pairs of these vectors are indeed orthogonal. So here is a simple example. We have the set here with 3 different vectors, and we're going to show that the set here is an orthogonal set if vector 1 is given by this, vector 2 is as such, and vector 3 is as such. Now, as I've said earlier, the starting point is to make sure that you cover all the possible pairs and make sure that the dot product here is equal to 0. So let's say we try with v1 and v2. So we can write this in this notation. So here is 2, 1, negative 1 multiplied with 0, 1, 1. And so you multiply with each component here. So 2 times 0 plus 1 with 1. So second component with second component plus negative 1 times 1. And this will be 0, 1, negative 1, which is equal to 0. So this looks okay. Next is we need to consider vector 1 with vector 3. So that is another possible pair. So here we have again 2, 1, negative 1, and this is the dot product of 1, negative 1, and 1. So again 2 times 1, 2, 1 times negative 1 is negative 1, and negative 1 with 1 is negative 1. So 2, negative 2, 0. So this is okay as well. And finally, we have to consider the combination of v2 and v3. So 1 and 2, 1 and 3, and finally 2 and 3. So this will be 0, 1, 1. And then here we have 1, negative 1, and 1. So 0 times 1, 0, plus negative 1, plus 1, and this is clearly equals to 0. Therefore, since all possible pairs here are orthogonal, that means the result here of this inner product, the dot product here is 0. Therefore, we can conclude that, so here as a conclusion, so therefore, or as a conclusion, this particular set is an orthogonal set in this vector space. Okay, here is another example. Can you determine whether these two vectors are orthogonal? So since we only have two vectors, therefore we can just straight away check what is the result when you consider the dot product of the first vector and the second vector. So here we have 4, 1, negative 2, 1, 3, negative 4, 2, negative 4, and here is 4 times 3, 12, 1, negative 4, negative 4, negative 2, and 2, negative 4, and 1, negative 4, negative 4. Clearly, negative 4 times 3 is 12. So negative 12 plus 12 is 0. And because of that, we can conclude that the two vectors here are orthogonal. So that's the idea of orthogonality or orthogonal vectors. Now let's move on to a bit of theorem here. Here we have, this is a set of vectors. So here is a set. We have several vectors inside here. If this is an orthogonal set with non-zero vectors in the vector space here, then these vectors are said to be linearly independent. Now I'm just going to illustrate this idea with a simple diagram. I like to do that for some reason. So let's say I'm just going to call this set here as A. So A here consists of vector 1, vector 2, vector k. So this is the starting point. We have a set of vectors, which is A. And we need to ask ourselves or to check. So check, is A orthogonal? So check for orthogonality. Okay, check orthogonality. So how do you check for orthogonality? Remember, to check for orthogonality, that means you are checking that all the possible combination of the two vectors here will be 0. So that is the idea of checking orthogonality. Now, let's say that once you have done that, well, you check for orthogonality, there will be two possible results. So here it will be yes. Okay, so maybe what I can write down here is it orthogonal? Okay, so is it orthogonal? So if it is orthogonal, all the possible pairs here has to be 0 when you consider the dot product. So let's say the answer is yes. Okay, you have two possible answers to this question. This is no. Okay, so if it is yes, then immediately we can say that A is linearly independent. So that's the idea. So A will be said, or A is said to be linearly independent. Okay, here is the definition for orthogonal basis. It says here, for a subspace W of this vector space, orthogonal basis is a basis of W that is an orthogonal set. Now, how can we visualize this idea? Well, let's imagine we have this vector space right here. So this is the vector space. And let's say we have this subspace, and we're going to call this subspace as W. Okay. So what we have to do next is we have to, well, find the basis of W. So find basis. So how do we find the basis? Well, let's say we find the basis based on, you have to make sure that the set that we have here must spans. Okay, so it spans, the set or the basis here spans the vector space, and another one is linearly independent. So these are the two how do I say this, the two characteristics of a basis. Okay, it spans and it is linearly independent. So let's say you are able to find the basis, and we're going to call this basis with all the vectors here, maybe vector 1, vector 2, vector k. So you have managed to get the basis of W. Now, based on this result here, you should go on and consider, is this basis orthogonal? So that is the next question. And how can you determine if it is orthogonal or not? You have to, well, consider all the vectors here. Maybe I should just use a different color. In order to show that B is orthogonal, then all the vectors here must be, if you consider the dot product of all possible pairs, the result is 0. So that means we know Vi, Vj must be equal to 0. So all the vectors here. Okay. Well, is B orthogonal? Again, we can have two answers to this question. It can be yes, it is orthogonal, B is orthogonal. It can be no. So when it is a yes, so if it is a yes, therefore we can say that B here is orthogonal basis. Orthogonal basis. That means what it is trying to say is B here is not just a basis, but B is special, and we call it orthogonal basis because we have the characteristic of this here being orthogonal. Okay, so that's the idea. Now, determine whether the given vector here is an orthogonal basis. So in order to show that it is an orthogonal basis, we have to follow this process here. So what we have so far is we are at this stage. So for this question here, we are already at the stage of having a vector, a set of vectors. So let me just call this A. So A here is the set of vectors of vector 1, vector 2, and vector 3, and we want to know whether A is orthogonal basis or not. So according to this simple diagram here, we are at this stage. We are not sure if it is a basis yet, so we need to check whether it is indeed a basis. So we need to check if it spans and it is linearly independent. So that is where we are currently at. Okay, so now we are going to start off with checking, is it a basis? Okay, again, in order to be orthogonal basis, first it has to be a basis, and then we need to check whether the basis here is orthogonal or not. So that's the idea. Okay, so we're going to check if it is a basis, and there are two parts. the first part is, I'm going to call it part A. We're going to check if A spans this vector space. Okay, part A. And part B is A linearly independent. Okay, so there are two things that you need to demonstrate. So the starting point for this one here is to consider the combination, the linear combination of all these vectors. So maybe we can have C1 with this vector, so 2, 1, negative 1, plus C2, 0, 1, 1, plus C3, 1, negative 1, 1, and it has to equal to something and we don't know what that is, so I'm just going to call it X, Y, and Z. And here we can write down in this representation, we have 2, 1, negative 1, 0, 1, 1, 1, negative 1, 1, and here is C1, C2, C3. These are the unknowns that you have to find what the value is, such that the result of it equals to X, Y, and Z. Okay, so that is the starting point for part A, question 1. Now for part B, we can see that we have a similar construction where you have C1 with respect to this vector, then C2, C3, and the difference is that here it has to be 0 vector, so 0, 0, 0. So we can then consider this representation. Okay, and similarly, these are the unknowns, and we need to make sure that all the values here are 0 in order to demonstrate that A here is linearly independent. So I'm going to call this equation 2. Right, so let's say we focus on showing this part first, that A spans R3, okay? So based on equation 2, sorry, based on equation 1 actually, so based on equation 1 from part A, so this one, we can consider the augmented matrix. Okay, so the augmented matrix will look like this: 2, 1, negative 1, 0, 1, 1, and then here 1, negative 1, 1. And right here is X, Y, Z. Okay, so remember, we are looking to find the value of C1, C2, C3. Now next is, I'm going to just change, because this is already 1, so I'm just going to change the first row with the second row, and the result is 1, 1, negative 1, Y, 2, 0, 1, X, negative 1, 1, 1, Z. Now what I'm going to do next is I shall consider this to be 0. So R2 plus negative 2 R1. Well, 1, 1, negative 1, Y. So 2 minus 2, 0. 0 minus 2, negative 2. 1 plus 2, 3. X minus 2y. And here is negative 1. Oh, sorry. Also, we need to consider changing this to be equal to 0. So I'm just going to do it straight away. So here I have R3 plus 1 R1, negative 1 plus 1, 0. 1 plus 1 is 2, 1, negative 1, 0, z plus y. Right, next what I'm going to do is I'm going to turn this into value of 1. So negative 1 over 2 times with the second row. So I have 1, 1, negative 1, y. So here is 0, 1, negative 3 over 2, x minus 2y over negative 2. And here is 0 to 0, z plus y. Okay, what I can do next is I can consider turning this value to be 0. So that will be R3 plus negative 2 R2. Okay, and here I have, well, 1, 1, negative 1, y. 0, 1, negative 3 over 2. Here I'm going to simplify this as 2y minus x over 2. So that is 2y. Okay, so negative is eliminated. We have 2y minus x over 2. Yep, and then 0 minus 0 is 0. And then 2 minus 2 here, 0, 0, negative, positive, negative, negative, positive, so here is 3. And over here I have, well, z plus y minus 2, okay, times with this guy. Well, it is x minus 2y over negative 2. Okay. Okay, so how can we simplify this part here? Okay, I'm just going to try and simplify that first, because here it looks a bit complicated. So here I have z plus y. This one can be cancelled out, so positive, positive. So plus x minus 2y, and here it becomes z plus x minus y. So it can be simplified as such, z plus x minus y. Okay, so let me just erase this. Okay, so the answer for that one here is z plus x minus y. Right, and I'll go on and continue with this operation by changing this value to be equal to 1. So that will be multiplying 1 over 3 with the third row, and the result that I will get is 1, 1, negative 1, y, 0, 1, negative 3 over 2. Here is 2y minus x over 2. And finally here is 0, 0, 1, z plus x minus y over 3. So this is the REF, and I'm just going to stop right here. Okay, and based on this we can then come up with equations, and we can solve x, c1, c2, and c3. Okay, and for that I need some space, so I'm just going to erase everything else here and just leave the final look of our REF matrix. Alright, so now consider this last part. Okay, so here we can straight away get the answer to the value of C3. So C3 is just Z plus X minus Y over 2. That is C3. And based on this, it means we have C2 minus 3 over 2. C3 is equal to, well, this is 2y minus x over 2. C2 is just, well, I can simplify that with y minus x over 2 plus 3 over 2. C3 is the whole thing, z plus x minus y over 2. And if you simplify that, you will get y minus x over 2. Here will be here is 3 over 2, and this is 2y. So z plus x minus y over 3 for this one. Sorry, this is not over 2, this is over 3, and here is over 3, okay? Yep. Now y minus x over 2. So here that will be plus z over 2. And then plus x over 2 and negative y over 2. So y and y, this will be y over 2. And then negative x over 2 plus x over 2 is gone. And then here we have z over 2, which we can write it in terms of z plus y over 2. Okay. Oh, we don't need a bracket, so we can just leave it at that. Okay. So that is the value of C2. And next is the last one here. We have C1 plus C2 minus C3 is equal to y. So C1 is y plus C3 minus C2, y plus z plus x minus y over 3 minus C2 is z plus y over 2. If you try and simplify all the items given here, you will get y minus z plus 2x over 6. So these are the values of C1, C2, and C3. Okay, since we have managed to get the values of C1, C2, C3, therefore we can consider writing the linear combination as such. Okay, so here since it is possible to find the values of C1, C2, C3 such that now we are going to substitute C1, C2, and C3 into this linear combination here, this one. Okay, so such that we have y minus z plus 2x over 6 with the first factor 2, 1, negative 1 plus C2 z plus y over 2 with the second vector is 0, 1, 1, and C3 is plus z. So this is C3. Okay, let me just erase all this. I don't need this anymore. Oh no. Well, okay, here I thought I've lost it. Okay, hang on. Okay, so okay, so such that this is the third vector, which is 1, negative 1, and 1. So if you consider this linear combination of all these three vectors, the result here is going to be x, y, z. So here are the values of C1, C2, and C3. Therefore, we can say that the set here, I've already named the set here is A. So therefore, A spans vector space of this one. Okay. So that is showing the first part of whether the given set is a vector, is a basis or not. Okay. Now we move on to showing part B. Okay, so now for part B, consider equation 2. So equation 2 here is all the matrix given in this way. So here we have hang on, where are the matrix? So here we have 2, 1, negative 1, 0, 1, 1, 1, negative 1, 1. So here is C1, C2, C3. This is vector 0. Consider equation 2 in showing whether A is linearly independent or not. Okay, so this is the starting point. Now you have seen that we have gone through a lengthy process to show this part, and you can see clearly that equation 1 and equation 2 here are not much difference. So if let's say we consider, or if we let's say we consider x, y, z in equation 1 to be set to 0, then equation 1 will be similar to equation 2, which is the starting point of showing whether the set here is linearly independent or not. And therefore, we can just consider the solutions given in part A, okay, which is related to equation 1, and just let x, y, z equals to 0. Okay, so based on solutions given, we can see that C1 here is y minus z plus 2x over 6, and if you let x, y, z equals to 0, that will be 0 minus 0 plus 0 over 6, which is just equal to 0. C2 is z plus y over 2, and since the values here are 0, so 0 plus 0 over 2 is 0. C3 z plus x minus y over 3, and this is also 0 plus 0 plus 0 over 3, which is equal to 0. Since the solution here, or the solutions obtained, are trivial solutions, therefore A is linearly independent. Okay, so what we have got so far is, according to this diagram, we have shown that we have a basis, and our basis is called A. So we have only reached this part, so now we need to check if it is orthogonal. Now if you look at this example here, this is the same example which you have already done at this stage, and we have already shown that this is orthogonal, so we can just use the result. But of course, if you have this particular example on its own, then the second step here is you need to show that they are indeed orthogonal. So you need to show that vector I dot vector j is equal to 0. And once you have shown that, so is it orthogonal? Yes. Then you can conclude that B is orthogonal basis, that vector is orthogonal basis. So in our case, what I can say is, well, I don't have space. So let's say I erase this part. Okay, maybe I just write down a bit of conclusion here. So what we can say here is, so the next part is to show that basis A is orthogonal. Okay, and you have to show that basis A is this one, V1, V2, V3, the product of the dot product of this all possible pairs 0, and so that means you have to show that vector 1 times vector 2 0, vector 1 vector 3 0, vector 2 vector 3 0, and we have done this example here, and so we can just use the result. Okay, and because of that, we can conclude that since everything here is 0, we can conclude that A is an orthogonal basis. Okay, because this part here, all the vectors, the dot products of all possible pairs here are all 0. And that's all, I think. Okay, so that is the process. Again, let me just emphasize the process of showing it is orthogonal basis. The process is, we need to find the basis first, or we need to check whether it is a basis. Okay, so here we have vectors. So we have a set of vectors, and we need to check if it is a basis. So basis means it spans and it is linearly independent. So once we have make sure that it is a basis, then we go and check, is it orthogonal? If the answer is yes, then we can call that basis, we can call this basis here as orthogonal basis. We can be more specific. Okay, so that's it. I think that sums up the idea of orthogonal basis. Thank you very much for watching, and I'll see you in the next video.